Hello, this is Dr. Russ. This is Chapter 11B, the second lecture on correlations. So this lecture covers the same content as on Lecture 11A, except that one was on whiteboard and this shows it on slides in case you find it easier to read. And the Pearson R formula is given at the end of this lecture, although we will repeat it in later lectures. So as you know, this is the depiction that we had in the previous lecture. And now let's just look at it here. So once again, a scatter plot is a display for correlational data showing the relationship between two variables. And so in this example, we'll use minutes of exercise for the X variable and happiness for the Y variable. And we'll put on the x-axis, the x variable, minutes of exercise, and you can see I have it laid out from 0 to 60 minutes. And the y variable, happiness, we'll put onto the y-axis. You can see it's labeled here, and it's got numbers from 1 to 10. And we have a number of people in our sample. We have person 1 who exercised 60 minutes a day and had a happiness score of 9. And there is that person's point. You can see that we travel upward from the 60. We travel over from the 9 to mark the coordinate. Person 2 had 30 minutes of exercise and a happiness score of 4. Person 3 had 40 minutes of exercise and a happiness score of 8. Person 4 had 30 minutes of exercise and a happiness score of 6. And if we continue to gather data from people, we might end up with a plot looking something like this. And you can see, looking at this, that the points generally travel in an upward direction. So we know this is a positive relationship. And if we were to draw in a line that came closest to the greatest number of points, it might look something like this. And this little graph can tell us much of what we need to know. The direction of the relationship depends on the trend of the points. In this case, they go upward, so the relationship is positive. And the strength of the relationship is calculated by figuring approximately the distance of each point from the line, with higher scores being associated with the points being closer to the line, and lower scores, lower strength scores, associated with the points being farther from the line. We have three types of relationships. We have linear relationships in which the points follow a pattern for which a straight line best describes the trend. And here we have an example of a positive linear relationship. Linear because a straight line fits the points best, and positive because they go upward. Here we're hypothesized to have age and stability. As age increases, we would expect stability to increase. And as age decreases, we might expect stability to decrease. And of course, we know this would not be true for every individual. We can't use correlations to determine that. All we can say is the likelihood. The likelihood of a person being more stable might correspond or relate to their age. We can also have a negative linear relationship. Here you can see the points go in a general downward direction. And so as one variable goes up, the other goes down. And here the posited variables are age and muscle mass. So as age increases, muscle mass decreases. We know this is true of most individuals, and so it might be a fairly strong negative relationship. A curvilinear relationship is one in which the points follow a pattern for which a curved line best describes the trend. And you can see in these two examples, the inverted U and the U, that these are both curvilinear relationships. The first one hypothesizes a curvilinear relationship between the X variable arousal and the Y variable performance, so that at arousal levels that are too low, like a person hasn't had their first cup of coffee and they just woke up, their performance might not be the best. But conversely, if their arousal is too high, they drank 3 cups of coffee and a couple of those highly caffeinated drinks that are sold at the gas station, well, they might be too jittery and their performance might not be the best. In order for their performance to be the best, they probably need an arousal level somewhere in the middle. Likewise, a fairly strong relationship suggests that if we put age on the x-axis and happiness on the y-axis, that younger people would be somewhat happier and older people would be somewhat happier, and the years in the middle where people are trying to find their way and just raising their children and very busy with work might have slightly lower happiness levels. Finally, we can have a zero relationship in which the points don't seem to follow a pattern at all. I wouldn't know which way to draw a line if I was to draw a line through here. The variables seem to be independent or to have nothing to do with each other. An example might be the number of keys people own and the test scores they achieve. We would not expect any relationship between these two variables, and maybe that's represented in a really ambiguous distribution of points. So a little bit more about positive or negative relationships. One thing you're asked to do is to predict the direction of the relationship. Would it be positive or negative? So if we had the number of pet dogs as one variable and the y variable, the money spent on dog food, what direction would you predict? I would predict that the relationship would be positive linear. As the number of dogs a person owns increases, I'd expect that y, the money spent on dog food, would also be predicted to increase, and vice versa. As the number of dogs decreases, the money spent on dog food would also decrease. Number 2, high school grades and college grades. What direction would you predict? As high school grades increase, would college grades also increase? Or as high school grades are higher, would college grades be lower? I would predict, and what most studies find, is a positive linear relationship. If high school GPA is higher, college GPA would also be predicted to be higher, and vice versa. If high school GPA is lower, college GPA might also be lower. Number 3, hours of video game play and grades. I don't know what you would predict, but do you think that as hours of video game play increases, would grades increase or would grades decrease? I predict that grades would decrease. This would be a negative linear relationship. As x, hours of video game play, increases, we would predict that y, GPA, would decrease, and vice versa. And finally, 4, the number of children a person has and the weekly hours they devote to self-care, things like exercise or massage or some other things like that. I would predict that as the number of children increases, the weekly hours of self-care would decrease in a negative linear relationship. So as when a person has more children, variable x, they have less time and money to devote to self-care, and the vice versa. With fewer children, they have more time to devote to self-care. So the Pearson R-value. The Pearson R-value is how we measure correlations. It will be a number between 0 and 1 with a positive or negative sign. If it's positive, there would be no sign, but there would be a negative sign, and that would represent the strength and direction of the relationship between two variables. So direction is measured with a positive or negative sign that indicates the direction of the trend line. If the line goes in an upward direction, it's positive, and there would be no sign there. And if the trend of the points is downward, it would be negative, and we would see a negative sign. Strength is measured on a continuum between 0 and 1, with 1 being a perfect correlation where every single point is exactly on the trend line. And this again shows the strength measure, 0, 0.2, 0.4, 0.6, 0.8, and 1. Any score higher than 1 is impossible. There's a calculation error. 1 is as high as it could go. And we might have 0 correlation, scores that are down here, small correlations in this range, moderate correlations here in the center, strong correlations around 0.8, and perfect correlations at 1. And remember, strength and direction are independent of each other, meaning that we can have a strength score of 0.4, and if we put the negative sign in front of it, giving us a Pearson R value of negative 0.4, the strength is still 0.4. all the sign tells us is the direction, and a correlation of 0.4 and negative 0.4 are both equal in strength. The plus or minus sign in the correlation coefficient represents the direction of the relationship. A positive, which may have a plus sign but more often has no sign, means the direction of the plot is upward to the right. As one variable increases, the other also increases, like this, a positive correlation between the number of hours spent revising and the exam results. As numbers of hours revising increases, so does the test scores. A negative with a negative sign always means the direction of the points is downward to the right. This also is called an inverse correlation. As one variable increases, the other variable decreases. An example using the British terminology is the number of flu jabs given, we call them shots here, and the number of people with the flu. So the more number of flu jabs are given in a community, the fewer or the lower the number of people with the flu. That's a negative correlation. Make note that negative does not mean bad or weak, and positive does not mean good. That's a common mistake, but don't get confused with it. In this case, you can think only in mathematics, with positive being upward direction, they vary in the same direction, and negative meaning they vary in the opposite direction. The number in the Pearson R value, as opposed to the sign, represents the strength of the relationship, and the strength refers to how closely clustered the points are around the line of best fit. So if all the points are exactly on the line, it's a perfect relationship with a strength value of exactly 1. And it can have a positive or a negative sign and still be perfect. Here's an example of a 0 correlation. There's not much relationship there. And you can see that the strength ranges from this 0 range, weak relationships or 0 relationships, all the way up to the 1, the stronger relationships, and that perfect negative and perfect positive. In both cases, the score of 1 indicating a perfect relationship, irrespective of the sign or the direction. So how do we interpret the correlation coefficient? Well, we have some guidelines. First of all, a strong relationship would be considered to have a Pearson R value of plus 0.8 or minus 0.8. And you can see here that both of these would be considered strong relationships. If you can imagine the line of best fit, you can see that it would be pretty tight to those points. And in the strong negative, it's even stronger because these points are even closer to the line. We can consider a moderate relationship to be these in the second row. A moderate positive would look something like this. You might think that it looks similar to this top one, but because the top one has more points, we actually do have a moderate relationship in this lower one, and a moderate negative, you can see the way the points are clustered. A weak relationship would have a Pearson R value around 0.2 with a plus sign or not, with a negative sign or not. And you can see what the point clusters might look like. Now, once again, these will all depend on the number of points in the distribution, and the more points there are, the higher the correlation score will tend to be. So let's just note that here, the more participants we have, the higher correlation coefficients. And if we have a number less than 30, often we won't get very strong R values unless it's a really strong, true relationship. And the last thing, saying it one more time, the strength of the relationship does not depend on the sign. An R value of 0.5 is equal to an R value of negative 0.5. Perfect correlations look something like this, look exactly like this, because there's only one depiction. Every single point has to be exactly on the line. In this case, the example given is age in years and age in months. If you know somebody's age in years, you can exactly know what their age in months will be. And so the relationship is perfect. You can perfectly predict every time, and the R value will be 1. You can also have a perfect negative correlation. In this case, the line isn't drawn, but you can see that every point would be exactly on the line. And the example would be weeks in the semester completed. If the semester in this example has 15 weeks and a person has completed 10 of them, we know exactly the number that they have to go. That is to say, if the numbers were lined up properly. We would know that if we knew the weeks completed, we know exactly the weeks remaining. And so that's what it means. We can perfectly predict an individual score on one variable if we know the score on the other variable, and we know the correlation coefficient, the R value, will be either 1 or -1. They're both equally strong. This correlation guessing game you will receive specific directions for and an example of in the next lecture. You will be changing the number of points to at least 30. You could go up to 50. And you'll be tracking your data by checking this box and doing 10 examples with the hope that your performance will improve with each trial. The formula for the Pearson correlation coefficient is fairly straightforward, although there are a number of steps along the way. But in a nutshell, it's just the average of the cross product zx, zy. And what this means is the z-score for each individual on the x variable. You know how to calculate z-scores from earlier in the semester. And then you're going to calculate the z-score for each individual on the y variable. And you're going to multiply them together to get the cross products like this, zx, zy. And you'll sum up the cross products and divide by n. So you're going to start by transforming every individual score to the z-score using the formula from earlier in the semester. You'll then calculate the cross products for each pair of z-scores, so the z-score for x, the z-score for y for each individual. And then you'll sum those cross products and divide by n. And you'll have your Pearson R coefficient. Now that will involve calculating the z-score. You know this formula, z equals x minus m divided by standard deviation. And this is what that whole formula looks like. And that's the end of what I have for you here.